Thank you for the invitation and the opportunity to talk at the PrimeKey Tech Days. So feel free to interrupt me anytime if you have specific questions. Today I would like to introduce to you the concept of Agile cryptography, and I would like to show you that the way cryptography is used by the industry needs to change. So cryptography is the foundation of the security, of digital security, right? If there's no cryptography, we don't have any IT security. It's in every systems nowadays. You have network protections using cryptography. You have all our devices, our smartphones are constantly executing and computing cryptographic operations. We have cryptography in the cloud, in servers, in the payment system rely on cryptography, traffic system relies on that, etc., etc. So it's everywhere, and it will continue to be everywhere. And now with IoT, people are realizing that we also need in the IoT space more cryptography to make it secure, etc. So it's the most important building block of every security system. But what happens if the foundation becomes insecure, right? So if cryptography becomes weak and insecure, then the security system breaks. We have financial loss, we have public safety at risk, data loss, compliance issues, etc. People are losing a lot of money. Sometimes the health of people can be endangered, etc. So the impact of weak cryptography is really huge. If something goes bad in the foundation, we have to deal with it. We have to deal with it quickly. And if you're not doing that, then everything is really bad. And that's what I would like to talk today about, how the industry can change and how industry can adapt more easily and cost efficiently to new cryptographic advances, to new threats, and make the system secure again in as fast as possible way. So what are typical risks, right? They just had 4 examples which happened in the last few years. One is most recent one is trusting crypto originators. So all people in the PKI system, you have to use certain standards, crypto standards, right? But there are still use cases out there, and I was really surprised to read that people are still writing their own crypto code, which can be devastating in result. In this specific example, they wrote their own hash algorithm, which turned out to be very weak. And the whole IoT blockchain thing had really a really big issue. Then we have the risk of aging of cryptography, which means here SHA-1 is the best example, right? SHA-1 was academically broken over a decade ago. Cryptographers were urging the industry to switch to SHA-2. It took a while, it took very, very long. People are still using SHA-1 nowadays, but just recently it was the first practical SHA-1 collision was published, which means now it's really, really time to switch away from SHA-1 to SHA-2, for example. Then you have the issue of vulnerabilities. So either it's a protocol vulnerability or it's a vulnerability in a specific implementation of a cryptographic algorithm. It usually takes very, very long to find it out, right? The system is at risk during this period of time, and a lot of bad things can happen during the time. So you need a way to react, to identify those vulnerabilities much quicker and to react to those much quicker. And then we have all this migration, mitigation risks, what comes into play when you really need to switch now to SHA-2. Especially those people in the PKI industry are aware of how time-intensive and costly a switch from SHA-1 to SHA-2 is. If you have a CA running and still using SHA-1 as a hash function, their certificates, then you need to basically rebuild the CA, basically. With a different hash algorithm, you need a different root certificate, etc. So those are the typical risks, and we see that those things happen. Most of the people are not aware that cryptography changes over time, right? Things are invented, new cryptographic schemes are invented, vulnerabilities are found, etc. So we need somehow to cope with this development and mitigate those risks. So, but it's not only about weak crypto. If something gets broken, if you have a vulnerability, we also need to have a look what else in the crypto space we need to think of when we are developing products, when we are selling products to customers and saying that they are safe. So they're much more than just weak crypto, and for that we have to look at how actually crypto evolved, right? And we go let's start in the 70s, right? You will mainly see that there are two types of events happening, right? Either a new cryptographic technique is invented, and with that, new cryptographic standards are published, or new cryptanalysis techniques are invented, and existing crypto algorithms are either broken or weakened. So there's, in the 70s, the most important one was the invention of RSA, changed a lot in the crypto world. Then some examples are that elliptic curve cryptography was discovered in the 80s, right? Then there was the first encryption scheme for mobile phones was developed and weakened on purpose. Then we had MD4 as one of the earliest hash functions published. Phil Zimmermann released BGP, etc. So a lot of things have happened. So RSA was invented. Many years later, 1991, the first RSA with 100-bit was factored. So we see there is a constant progress in either in inventing new cryptographic algorithms and therefore also publishing new cryptographic standards. And also there's a progress in cryptanalysis where we cryptographers try to find weaknesses and improve the existing schemes. So other important events were SHA-0 was published, it was broken immediately, then SHA-1 was published, etc. So later on, so basically in the 70s, they started, cryptography is very old, right? The Romans used it, but and many other societies in the past used cryptography, but the most use of them was in the military, so right? Even in the 19th century and in the early 20th century, it was a military technique, right? People were using cryptography to secure the communication system, etc. I think in the 50s or later, that turned to be a public research topic. Cryptography became usable for the public domain, and with the invention of RSA and similar techniques, more and more people were able to use, and with the move in the information age, in the digital age, it has become more and more urgent that we are using cryptographic techniques to secure our systems. So most important things happened in the 2000s, in the early 2000s was AES, the Advanced Encryption Standard was published. After the AES was broken, NIST had to publish a new standard, and that was the first public competition to find the new encryption algorithm. DES was still developed by NIST and NSA, but AES was not the first one which was open to the whole process was open to the public. Every cryptographer were able to submit his own proposals, what could be the next block cipher, and the design Randall won the competition, and it was standardized as AES, as the Advanced Encryption Standard. At the same time, more standards were published and more success in the cryptanalysis was happened, especially in the hash function era, right? So we were showing SHA-1 was academically broken in 2005 to show there were specific techniques that were able to create collisions, which takes less effort than it actually should. There are some boundaries. Every hash function should some security boundaries they have to fill. It's below that. And after a while, NIST realized we need to replace SHA-1, right? And they first had previously already introduced SHA-2, but SHA-2 was related to SHA-1, right? It was basically, simply speaking, is a bigger version of SHA-1, right? The same similar building blocks, the same design methodology was used for SHA-2, and it was also developed in secrecy. So they announced the SHA-3 competition in 2007 to do it in a similar way they did for AES. It's a public competition, everyone can submit something. It runs for a couple of years, and all the cryptographers and all the communities out there were looking at different proposals and tried to break them and make them secure. And not so long ago, they published just a 3 standard as a replacement for SHA-2. Then there were other techniques. So we had MD5 was standardized, was published, I think, in the 90s. Then it was broken, and in 2005 we had actually the first practical collision for MD5 in a X509 certificate. So this should show you that usually MD5 was academically broken. and usually cryptographic attacks get better, not worse over time, and it's just a matter of time until you have some practical attacks, and in that case, they were able even to forge a X5909 certificate. And at the same time, people are also investing time in breaking old algorithms in more efficient. 2017 was this finally broken just in 25 seconds. So instead of a couple of months and then later days, now it's really a matter of seconds to break the ES. And the most recent, most important was that we had the first practical collision attack on SHA-1 this year. Everybody was expecting it. The crypto community was expecting just a matter of time, time and resources to invest until we can show that now it's really broken and you really need to switch to something else. So that's basically what happened in the last 40 years, right? I apologize for those people who are not mentioning here in those results. There's a lot of things, that's just a small fraction of what happened in the last 40 years in the crypto space, in the crypto community, but I think those are kind of one of the key points here. So we see it as constant progress. So what happens in the future? Obviously, it's hard to predict, but we know that there will be IoT standards and regulations, right? They might regulate the way cryptography is used, what kind of algorithms might be used. Then there might be lightweight cryptography standards. There are already some standards out there in the light crypto space, and there's something like a functional encryption. So there are different things, different crypto techniques and algorithms are getting invented, as happened in the last 40 years. This will continue and will continue for the next 40 years as well. Then, most importantly, we have post-quantum cryptography standards, most likely in the future, right? So NIST starts a new competition end of November for post-quantum crypto algorithms. So we know for sure there will be some standards in the near future. There's homomorphic encryption, there are multi-party computations, there are a lot of things which will happen in the next, in the near future and farther future. But also, the cryptanalysis techniques will also improve. It's just that the invention of new cryptographic algorithms. We might see a forged SHA-1 certificate, like in the MD5 case. It took some years until they were able to do that. We have now practical issue for SHA-1. Might be the case that in some day in the future we will have a forged SHA-1 certificate. What about SHA-2? People are investing in analyzing SHA-2 and its security. We don't know yet. And what about RSA and DSA? And ECDSA and liquid cryptography, which will be broken with the upcoming of quantum computers. So we know from the past that stuff progresses, research progresses, new stuff gets invented, old stuff gets broken, and we know that will continue. And there's a lot of different type of cryptography we need to be aware of. So you saw there's a lot of different things, but how diverse is crypto? So especially in the PKI industry, you know you have a hash algorithm, you need a signature scheme, and the appropriate keys, right? That's it. But crypto is very, very broad. There are all kinds of different things. You can just a few examples. We have traditional crypto, those algorithms you're using, we are all aware, liquid cryptography, AES, RSA, DSA, etc. Then we have something called lightweight cryptography, which its purpose is to be either computational efficient, power efficient. So you have in the IoT space, you might have very small devices which run on battery. So you cannot have RSA running on it because the battery will deploy rather quickly. So there's a whole research track where people are investing and try to find crypto algorithms which are fast or don't need a lot of power on those small devices. And this will become more and more important as IoT, whatever IoT means, gets deployed. We have wireless sensor networks which need to have secure communication if you read data, etc. Then we have national cryptography. The United States have their suite A and suite B. Germany has their own signature scheme. Russia has their whole set of crypto algorithms called GOES. Korea has their own stuff. China has it, etc. And more people are, and more nations try to have their own cryptographic algorithms and standards. And then, very important is post-quantum cryptography. Now, we need to have new techniques to withstand quantum attacks, right? So there are basically 5 types we already know of: code-based, hash-based, isogeny-based, etc. So these are completely different algorithms relying on different mathematical problems as ECC and RSA. and their purpose is to, once quantum computers are out there, they will withstand any attacks to them. And obviously, we need to already think today about that. So why should you care, right? You are not a cryptographer, or are there? I don't know. You see, we have constant progress. Stuff gets weak. Implementation can be vulnerable. There's very, very broad spectrum of type of cryptography. If you develop a product for a specific use case, for specific customers, you kind of need to be flexible because, especially now going in IoT space, use cases are very different. They might be different needs. If you develop a system which should have a certain security, you don't want to have for each use case or each type of cryptography their own system to maintain everything. It's rather costly and time intensive and resource intensive. So ideally you just have one product and you have rely on whatever cryptography can be plugged in later on. So we need sort of agility in this concept, right? So nowadays, if you look at applications, how they're using cryptography, they either have their own, they use a specific crypto library, but it's kind of hard-coded in there, right? You use ECDSA for signature scheme. In your code, you write down what you actually want to use, which keys, etc. But you need to be more agile because of those things I just told you. Either you would like to support or go into and sell your product in countries which have specific regulatory requirements about what crypto you want to use. Then you would like to be able to react on cryptographic threats. Let's say one algorithm gets broken. More likely is often that you have a vulnerable implementation of a specific algorithm. So you must need react very quickly and fix those issues. And today that's very hard. If you look at the future, let's talk first about longevity of IoT. As we heard today, those devices are often 10 and longer than 20 years in the field, right? They're there. They might use cryptographic algorithms which are safe today, but if you already look at quantum computers and you have a IoT device operating for the next 20 to 30 years, there will be someday an issue, right? And you can either replace the device when it's the case that you need to replace it, but those things are out there, not every time easy reachable, not often it's not very easy to update critical components like the cryptographic algorithms on these devices. So you need agility there as well. You need to be flexible to react and to adapt to new situations, especially for devices which operate for a very, very long time. And then we have the future of crypto, right? We know quantum computers will come. We don't know when, depending on who you ask. You get different predictions. But there is certainty that there will be someday quantum computers, and then they break all our classical public key systems. So you need to be prepared for that, right? You don't want to have the situation that you are having a system deployed, and now quantum computers are available, and now you need to switch, etc. Because they will really break security really badly. So, and I suppose quantum is really the best example, although it might be in the future, but you already need to think now about how you protect your data, because everything recorded today, everything encrypted today, using, let's say, ECDSA as a signature scheme, or ECD-Helm as a key exchange, those things will get broken later. So we know that certain government agencies are recording everything which is flowing through the internet, so whatever they record today, they will be able to decrypt later. So that's already a problem here. And you have in certain industries certain requirements, regulatory requirements that your data needs to be safe for 20, 30 years or even longer. So you need to think today how you will react on that. And that's also where you also need to have certain agility in the cryptographic layer of your application. So what can we do, right? So we have a problem. A lot of applications, let's say most of the applications, changing the crypto core is time intensive. You need special know-how to do that. You have a lot of deployed systems where you need to do that. Pushing out updates might work very easily for a laptop, but it's much harder for devices which are deployed and operate for a very long period of time. And that's where we basically introduced this cryptographic agility concept. So it's the ability of a system to easily adapt to alternatives to the cryptographic primitive it was originally designed to use, right? So how agile your system, crypto agile system, the application is, depends on when you now need to switch to a different algorithm, how easy it is. Is it just a push of a button, or do you have a long migration process which goes over a year or two? And the longer the process takes, the longer you have risks for attack, the more costly it is, etc., etc. So how can we achieve this cryptographic agility? And the goal is, and what you have to do is, we need to decouple cryptography from applications. Like we have operating systems, you're right, we have an application, it runs an operating system. The same thing should, or a similar thing should happen with cryptography. Application shouldn't be longer tied to your cryptographic core, right? It should be very easy replaceable without ever touching the application again. So the application has some certain functionality and the purpose, and the crypto part does, again, a specific functionality, but it should be replaceable, it should be easy to switch, and it shouldn't be necessary to change your application or application code. So what should have, right? The first thing you need to, in order to make it work, is you need an abstract API, which means instead of calling specific cryptographic algorithms like AES or ECDSA, you would like just to have an abstract API which just says sign specific data or encrypt. And what actual algorithm is used below is determined by a different layer. It should be dynamically loadable, which means I don't want to power off the system just to migrate to a different algorithm. The system is down for a couple of days or even longer, right? So it should be just the system is running, you can easily deploy a new algorithm, and the application just dynamically loads the different set. It should give even more fine control, so you should be able not just to select a specific algorithm, but also a specific implementation type. So there's a lot of side channel attacks on cryptographic implementations. There are countermeasures against it, but countermeasures often come with a certain cost. And you have to check, okay, is speed or performance more important in this specific use cases? And then I need to switch very easy and dynamically between different implementations. And if you really need to deploy now a new algorithm because of a new standard, because quantum computers have broken your system, it should very easy and really just a push of a button to switch to push out new cryptographic algorithms without touching your application code. And as Scott was mentioning, it's not just the technology, you need to also have a sort of manageability of the system. It should be, there should be processes in place which decide when and how cryptographic algorithms are deployed. You need expertise in that area, so with cryptographic agility, it's much easier to sort of outsource this part. More companies than cryptographers of the world, everybody needs some certain expertise there. Either you buy it from a different company, and you need really those experts to make those decisions. You need some information of when do you actually know when you should switch. Not every company has the specific expertise in that area, especially if crypto is their core selling argument. And then, to make it really accessible, it should run on everything, right? As many platforms, it should run on a PC, on a server, it should run on a sensor, it should run on an industrial control device, it should run wherever possible. Just to give you an example how that looks like, so one early try to achieve cryptographic agility was basically the Java cryptography architecture. So it's a framework for Java where we have a generic API, like in this example. If you would like to use a specific hash function, you can basically have it as a parameter. You just say you want a hash function, you can then hash something, but you're only telling give me MD5. And those string can be in a configuration parameter, etc. What Java does, you have this provider concept that the actual implementation of this specific algorithm is encapsulated in a provider, and you can plug it in. If you don't like the crypto implementation of company A, you can easily switch to company B as long as they provide this specific provider interface. A downside of Java is it's Java with all the advantages and disadvantages. It doesn't run everywhere. There's no managing concept. You cannot manage what kind of providers you use. you would like to use. There's no management platform. You cannot choose specific implementation. The whole process, how providers are built and how you can get it included in your application is not straightforward. So it's a good try, but we need something better, right? So what about PKI? So since we're a PKI community here, let's have a look at how agile is actually our PKI system. And we actually saw it's not very crypto agile. So we have usually an HSM where you have your key generation, you have a software like EGBCA, and then you have the certificates, kind of the end product of the PKI system. There's no easy way to switch algorithms in HSM. You can get that by firmware updates, then depending if they have the certain certification, they might need to rerun through the certification process, but there's no easy way, nothing dynamically, you can just push out the algorithm, your PKI system doesn't have to shut down, etc. The same goes for the software stack, right? There is no easy way where you have a management platform and say, okay, now I really would like to use SHA-2, and I really just push a button and it gets pushed out to your EGBCA instances. And there's obviously no easy way to switch algorithms and certificates. They are very, very tight, very binded. But it's actually not that bad because we can do a lot of things. We can, in HSM and software, make the crypto updatable, configurable, manageable. We need to deploy the technology and make the people aware that they actually are needing that. So there, it's just really replacing the crypto algorithm. The application can then use whatever it should use. It's much, much harder than a certificate, right? What we would like to avoid is you have millions of SHA-1 certificates and you need to now replace them. That's how it is today, right? You have deployed a lot of SHA-1 certificates and you really need to create a new SHA-2 certificate for every device using it. You need to replace it, you need to go out to your deployed systems, first find out where actually I have SHA-1 certificates running. It's I heard a lot of use cases where that's not so easy. So what can we do there? And we basically need to look at different ways to make certificates. And one idea is that X509 is actually support crypto agility, right? Because the standard does not specify what algorithm or signature algorithm are you actually using. You can use it with anything. But still, meaning replacing a hash or signature algorithm means that you need to replace the certificates. So what we can do, that's an active research topic of our company, and one intermediate solution could be that if you look at different technologies, and there's one very interesting technology out there, it's called Cyan. I really encourage everyone to look up the web page. It's the technology is originating from ETH in Zurich, and they basically built a system to improve the current internet architecture. So the internet itself has a lot of issues, trust, security, and they propose how we can make everything more secure in a very, very smart way. It's a very, very complex system, and you can easily talk 2 or 3 days just about Cyan, but we are looking at one specific property there and one specific subsystem. That's their, they call it end-entity PKI system. So they're taking the issues we have and they solve it with a different PKI infrastructure so that they can have all this trust scalability, transparency, resilient, etc., etc. But we are now mostly interested in the agility concept. And if you're more interested in how this end-entity PKI system, this future PKI system could look like, look at their webpage. There are a lot of publications and presentation which explains in much more detail. So the end-entity PKI is based on 2 concepts. One is the RPKI, so attack resilient public key infrastructure, and polycert, so a different type of certificates. And we will look at polycert. So polycert has 2 different concepts, 2 different components. There's the subject certificate policy, which means that the domain owner, the device owner, defines the certain security requirements. It defines which CAs it should trust. It defines what should happen if I contact the domain and something goes wrong, the signature is invalid. The domain itself, compared to nowadays PKI system where that happens usually on a browser site, right? That gives the control to the domain owner. And then what we were looking at is the multi-signature certificate. So a different type of certificates which gives you much more security. And the main idea is that a certificate is signed by multiple entities. So in these policies, you can define a lot of security parameters. And what will come to date is that we can also add some agility concepts there as well. So multi-signature certificates, it's, let's say, a first attempt to get more agile certificates. So how the science system defines it is that you have a series of standard X509 certificates, right? All are signed by different CAs. In order that the certain multi-signature certificate is considered valid, a certain threshold number needs to be valid of those certificates. If you have just one certificate in a list, then it's just a regular X509. So what is about the agility? So the original concept of SIGN doesn't take multi-signature certificates and talk about the crypto agility, but if you have a look at that, and if you have already a couple of certificates there, is that instead of having a couple of CAs just signing different things, you can also use different algorithms for each certificate. You can have one with RSA, one with ECDSA, one with Sphinx, post-quantum crypto scheme, and one for national crypto. So you can have a couple of certificates using all different algorithms, and your security policy defines actually how you would like to validate and how you would like to what you would like to accept. So if it turns out RSA is broken, then you just set in a security policy that RSA shouldn't be valid anymore, and now the remaining 3 should be. So it's not originally designed with this idea in mind, but it could be a first step to achieve better crypto agility in certificates. So what next? So we know that we have to change how the industry is using cryptography. We need crypto agility because we need to cope with all the progress in cryptography. Cryptography things just get better, new stuff get invented. You need to be prepared to offer your products in various markets for various use cases. It shouldn't be costly to develop products just to have those different use cases for different algorithms. We need crypto agility to comply with local regulations. Might be specific algorithms in specific countries you have to use. Might be new upcoming regulations coming up. But you have to be adept to it. You shouldn't take a lot of development effort for the product developers to adhere to those new regulations. It should be in the ideal case that the whole crypto layer is managed by experts. You're just using the framework, and you can define then that you put the application out and somebody else can actually decide what crypto is plugged in. And we need to be prepared for future standards and challenges. We know quantum computers will come. There will be a reality in some time in the future, but you need to already be prepared now. So you need to adapt your application, and when is the case, when it really need to switch to a post-quantum signature scheme, it shouldn't cost you much, it shouldn't take a lot of time, it's just really ideally just a push of a button. But there are still many open questions, right? So the idea I just presented about Agile certificates, it's not so very elegant, right? You blow up the number of certificates, you need much more storage, and also doesn't help you if you have a new algorithm which was not there yet when you signed those multi-signature certificates, right? So we need some better way. And the goal for this certificate agility is that we define a new type of certificates which gives you all these properties you would like to. So once you deployed a million of certificates and you need to change an algorithm, that you don't need to replace all the certificates in your systems. But we also need to look at IoT, how IoT can be crypto agile, especially in the use cases where devices are deployed for 10 or more years. So we need to be prepared that, especially for those long periods of time, a lot of things can change in the crypto space. And you don't want to send your field engineers out and make a firmware update on every device out there. So you need a better system. And you need to prepare a system today that you are still secure in 10 or 20 years. And also blockchain is a buzzword, everybody is talking about blockchain, now we can use it. And blockchain is not crypto agile at all. So if you look at Bitcoin, for example, and all similar blockchains, they all rely on signatures and hash functions like in the PKI systems, right? So you have a huge blockchain all signed by, let's say, ECDSA. quantum computers are out there, the whole blockchain becomes invalid. So all signatures are forgeable now. So basically the blockchain is useless. So we need, if we really want to rely on such new technologies as blockchain, we need to think about crypto agility, especially those things which where data integrity is very important and should be safe for 10, 20, 30 years. So we don't want to throw all our bitcoins away just because quantum computers have emerged. All right, if you have any questions, feel free to ask them. Yeah.
I have a few.
Yeah, very quick. You mentioned that crypto market needs to adjust
application compatibility. What about performance? What about the validation XC that has the certificate? Now have it for different signature.
Given which type of needs to be used and realize that it will remain.
So we expect that regulations will start to force certain level of crypto agility. We already see discussions in NIST happening, right? That the whole FIPS certification is kind of not perfect. Once you have certified it, you're no longer to change anything. And even if you have a vulnerability in your software, you're not allowed to change it because you lose certification. So standardization bodies are thinking about how can that be done better, and we expect that crypto agility will play an important role there. You need to be flexible. The regulations might probably be define some certain parts that they are crypto agile, that it shouldn't be too hard to switch to something new, to new standards.
When we look at the elliptic curve-based cryptos, we have seen these for a decade or more, and still we have units that will support elliptic curve-based cryptos. How do you see, what's your view of quantum-based cryptos and the adaptation speed of that compared to that we maybe have quantum computers in a few years?
So you mean you have devices out there which are not even supporting easy elliptic curve cryptography? So existing devices, existing hardware out there which don't support even crypto we are already using now, they basically will need to replace. There's no, don't see an easy way that you can switch something, especially if they require some hardware acceleration or etc., or they're hard to reach. If you have certain control over the firmware, over the software which is running there, and you can actually access and update stuff there, then you can introduce crypto agility there. But for devices where you cannot do that, there will be a certain time where you need to replace them. And when you're replacing them, that's the key part here, then you already should replace it with something which has crypto agility built in, because you then can avoid this to have the same problem in the future.
Chava to go algorithm to break the asymmetric key of 20 years old. Mm-hmm. Are they some new algorithm to break these asymmetric key faster?
No, not that I'm aware of. You're right, it's quite an old algorithm. Still depends on building an actual quantum computer to run there. But what we expect is that the research in quantum computers and post-quantum crypto will take off, and people are investing more time, and we cannot exclude that there will not something be invented which is faster and sure, some different ways to do that. At the moment we are not aware of different things. It's already bad enough to let us worry, but things can change, and we expect a lot to happen in the next 5 to 7 years since NIST has started the competition, right? We will see by end of November a lot of different post-quantum crypto algorithms, and with that, research will focus now on this specific topic. More resources will put into the research of quantum computers and post-quantum cryptography schemes. And especially you see that quantum computers are not just interesting for cryptographers, right? They do a lot of good things, and companies like Google and others, they're investing a lot of money in building an actual quantum computer because they solve a lot of good problems as well.
As someone mentioned also this morning, that security versus usability. When it comes to multi-certificate, multi-signature of the same certificate, have you looked at also at the usability if you need to revoke a certificate for different signatures and you have just one CRL distribution point, how you can handle that?
It's done in a broader, there are concepts of science which take care of that, which I didn't explain, because already explaining all the details of PKI takes a long time. There are concepts to simplify this and make it usable, actually. So the whole entity PKI system, including other components of Scion, that will give you all the advantages and usability. So they thought of that. Just Crypto Agile is something new, and as I said, it's not the elegant way to get Agile certificates. There must be better ways, and we still don't have that yet, but we hopefully will have soon.
But your application should be prepared what kind of actual application, right?
Exactly.
And most of the application is not.
Exactly. So for those things, your application need to adapt, right? So first step is to design and invent the technology, and then you need to convince the industry and applications to adapt to it, right? The same goes for the Agile crypto framework, right? You don't get Agile by just doing something, right? You need to adapt to the new technology, and then you are prepared for these future things, right? The same goes for those multi-signature certificates. Your applications, your system, some other components need to be adapted to get the benefits from it.
Just the last question. Is there any comparison between actually the current situation, just having one, and the multi-certification? Have you done any pros and cons when it comes to a complexity that you provide to our actual vendors, operators, and users?
So for the whole science system, yes, there are some intermediate steps you can do, right? For the specific PKI, I'm not aware of some intermediate solutions. But that's just at the beginning, right? So we're just starting to invest time and resources to find alternative to these traditional certificates. More questions? All right. Thanks for listening.